So I want to start by closing off some loose ends. One of the issues that came up in the tutorial that was pointed out by Elliot is that the conditions that I said we should impose on the matrix X do not really imply that the matrix is used. So X went to X prime, U, X, U dagger. So the fact that the determinant of this has to be preserved and it has to remain traceless and Hermitian doesn't mean that U is in SU2, but that U is in U2. And the point here is that if you look at the U1 factor of U2, it actually has trivial action on X. The part of U2 that has non-trivial action on X is the SU2. Therefore, SU2 is the group that is relevant for the homomorphism that we're building. The second problem, I have rewritten it, and so those of you who attempted it, you can have a look, and then if you want to chat about it outside class, I'm happy to do that. The other thing I didn't have time to define yesterday is what an abelian invariant subalgebra is. So it's a subalgebra that commutes with everything, in the Lie algebra. If you define, after defining what an abelian invariant subalgebra is, one can define a semi-simple Lie group or Lie algebra. So it's a Lie algebra which doesn't have an abelian invariant subalgebra. It is not hard to show that an example of a semi-simple Lie group, Lie algebra, is the Lie algebra of SO4, because it actually breaks up into two Lie algebras, two different SU2s. Okay, so so today I wanted to touch upon a smattering of topics. Time is running out. I would hope to get to SU3, the representation theory of SU3. So so I will not be probably as thorough as I would like to be. So some say useful geometric concepts you can define a natural metric called the killing metric. This guy is killing it. On a Lie group, and to define it, we first define what a left invariant one form is. So this is a left invariant one form. So this is a and it derives its name from the fact that if you replace G by G times H times G, where H is in the Lie group G, but constant, meaning that the derivative operator, leaves it, doesn't act on it, then this object is invariant under this transformation. Now this thing is an element of it's a one form, so it's a cotangent space. So M is the manifold of the Lie group. It's also an element of the Lie algebra. We can similarly define a right invariant form, and that's basically dGg inverse. This is the right invariant one form. Then to define the killing metric, we consider this bi-invariant, which means that it's both left and right invariant object, which is trace of G inverse dG, G inverse dG. Obviously, by its definition, it is left invariant, but because the trace is cyclic, you can also see that it can be written, in this form. So it's also right invariant. Now, using the fact that this is a form as well as a Lie algebra valued object, we can expand this object. So there will be some. So suppose phi are the coordinates on my manifold. So because it's a one form, there will be something like a one form, the basis, and there would be the summed over those indices. It's also a Lie algebra valued object, so there would be an A, and that would be contracted with the generators A, and this thing should be a function of the coordinate. So now if I plug this into there and use the fact that G is some compact compact Lie group, so that I can I can normalize the trace of TA TB to be some constant time delta AB.
Can you explain T and phi again?
Oh yeah, sure. So phi are the coordinates on M, which is the the manifold. Well, sometimes I call it M, and sometimes I've called it G as well, right? The manifold of the Lie group. Sorry, of the Lie group G. And TA are the generators in the defining representation, in this case. So now if I plug this formula in there, I basically get and there's some constant, and there's a delta AB times d of phi mu d of phi nu. And this looks like a line element if I identify this thing to be a metric. So this is essentially what I've constructed is a line element on the Lie group. Yeah?
Sorry, just these G's over here, are they group elements?
Yeah.
And the H is also a group element, and when you say it's constant, are you saying that this is a left invariant under any transformation by any H in the group?
Right. Yeah.
And for a right invariant, would you be multiplying by H on the right?
Yes. So right invariant means that G, right. So
and DG is the element of the cotangent bundle?
yeah.
And then is G inverse an element of the Lie algebra?
Lie group. Okay. So let me break this down. Okay. Yeah. So suppose G is an element of the Lie group G, right?
Yeah.
And if I have a compact Lie group, I can always use the exponential map and write it as e to the power I something, right? And this belongs to the Lie algebra, right? So when I take the exterior derivative with respect to this guy, what I see is I basically so let's call this dot t, right? Then I would get G times I t dot this thing, right? I'm bringing down this object down, right, from the exponential. Okay. And right, so I can write this on this side, and right. So now G inverse will be given by well. So now if I multiply this guy goes away, and what I'm left with is t dot. Right. So this is the statement that this is in the cotangent bundle, which is given by this guy.
Okay.
And this is the Lie algebra, which is given by this guy. Okay.
So is that when you write dot there, is that like so when you write them, yeah. So the zetas are just
they're just the coordinates, right? Okay, I should call them phi, right? Because to be consistent, sorry. Let me call okay, I think
what is G?
sorry?
What is G?
G is an element of your group. It's a finite element.
Maybe it's group value, but it has to be a field over something for it to take that.
What do you mean field over something?
Wow.
Hang on. I think that okay.
D. So it's G of phi.
So can you repeat that?
It's G of phi. So because you're deriving.
Right. So I'm saying that. Okay. So what I'm saying is that my G is some group manifold. G is some group, and on that group I have some coordinates, right? So sorry. Yeah. So the phi's are okay. I think so. Yeah, there is some notation. I just introduced some bunch of notation here, but what I mean is that zeta are the parameters which parameterize your group element.
Your field of group elements.
field. I don't know what you mean by field of group element, but
To each value of the coordinates, you associate.
Right. It's a map. It's some coordinate map on some group element, and phi and the zetas represent the coordinate. So if I set all these parameters to 0, I get to the identity element. Right?
So why is phi wrong? Why cannot phi be there?
Sorry?
Why cannot phi be there?
Why cannot phi be there? Yeah, that's a good question because so in essence, okay, what I'm doing is I'm introducing what. So basically, so suppose you have some manifold, and you take some point, and you take a tangent space at that point. So and you have on the tangent space, some tangent vectors, and those tangent vectors, say, are something like right. Right. Okay. Sorry. So so if I kind of look at this part, so I look at EA mu of phi, D of phi mu. What I am, so this is basically these are the basis vectors in the coordinate basis, which I'm calling phi. This is the basis one forms in the coordinate, but this thing together is actually giving me some field of one form, say, I don't know, call that eta of A. So these are one forms, and so now the question is, how is that related to these parameters psi, zeta, right?
Is E a tensor that's defined by the group element G?
Sorry?
Is E defined by the group element G?
So the E is, so okay, what the E does is that it gives you a basis of one forms. It's basically an object which translates between like a basis of one form. So these one forms, what they do is that, so okay, so I was, suppose this is the cotangent space, and these one forms form the basis of the cotangent space. And as I as I move around on my manifold, I have different values of phi. And what these e's do is that it tells me how to translate between the coordinate basis, which is of one form, which is d phi of mu, and the and the non-coordinate basis, which is these eta a's. So in Cartan's language, this is basically a kind of a moving frame, if you like. So it's not obvious. So let me come back to what's the relationship between phi and the parameter zeta. It's kind of I'm not able to make that connection right now, but let me come back to that point.
What we're trying to do is build a real line that's canonical to the group.
Right.
And get the matrix.
Yes.
Build a Velbine, tetrad.
Yeah, moving frame, all that kind of stuff. So, so if you think of phi as being the coordinates on your map group, and then these are just some kind of coefficients, right? You can think of this as being coefficients. Now, hang on just 1 second. So I guess you can make the connection between these zetas and this by taking the trace of this object, right? So now so this is probably the answer to your question, is that if I now say, okay, I'm taking T of A and saying D of dg inverse, and I take the trace of this thing, then what I would get is that I'll get a delta from here, and so I will get some lambda times E of mu of A of phi, and then I would get D of phi mu. And if I were to do the same thing over here, I would get up to some factors of I. I will get I times D of zeta A. So so basically, this is going to be the relationship between between phi and the zetas. Right? Yeah.
So one last question. Well, there's actually two questions. I'm kind of confused about what object G inverse dg is.
Okay.
So TA is an element in the tangent space, and the d zeta A is in the cotangent space, right?
Right. Well,
Phi, say, is in the cotangent space.
yeah, I mean, right. So you can think of, yeah, you're right. So you can think of this as, so for matrix Lie groups, you can have an identification between the tangent space and the Lie algebra element. So here I'm thinking of the TAs more as being residing in the Lie algebra,
Okay.
and this as residing in the cotangent space.
Okay. But regardless, I don't understand what you mean by writing. Sorry, this is just my lack of understanding.
No, it's fine, yeah.
But I don't understand what you mean by writing the tensor product there. Like, I mean, if you like a cotangent or like a covector times a vector should just give a scalar, right?
Well, yeah. I'm not really taking the inner product between these two guys.
So what kind of, like, how should I understand this object?
So I think you have a point, but the best way to think about it is that, this is some matrix, right? So this is a matrix valued thing, and this is this is a one form, which is the usual way of. So I mean, I am kind of not at this point. I am thinking of this as just a Lie algebra, not as the dual space to the cotangent space. Okay?
I'm sorry, my other question, it's a small question.
That's fine.
On the top half of this board here, you use D, G, DG. So should one of those be inverse?
Yeah.
All right.
Yeah. So yeah. All right. Thank you for those questions. Okay. So this thing is called the killing metric. And if you are given a metric, you can always define a torsion-free connection called the Levi-Civita connection. So if I have G mu nu will give rise to some torsion-free. This is the torsion-free connection. This is called the Levi-Civita connection. It's also called the Christoffel symbol. This is not a tensor object, but the important thing here is that this is actually symmetric in these indices. Someone asked me if the Christoffel symbols were related to the structure constant. The structure constants give you antisymmetric. It's antisymmetric, so they are not directly related. However, there are other connections. So there are other connections on the manifold on G that you can define, and those connections are not torsion free. And the structure constants do contribute to them. But we won't go there. It just involves too much formalism. So I wanted to close off the part about geometry by talking about the action of groups on manifolds. So I wanted to talk about group actions. And so what is a group action? So let G be a Lie group and M is some manifold the action of G on M is a map that goes from G times M to M such that the group action of the identity element on some point P, on point P is P for all points of the manifold, and that the group multiplication law is implemented in this way, that if you apply G2, G1 on P is the same thing as applying G1 first, and then applying G2 on the result of that. So group actions can have different kind, there can be different kind of group actions. So it can be transitive. So if for any P1 and P2 in M, there exists an element G in my group such that we can reach P2 by applying that element on P1, then the group action is called transitive. A group action is free if for G, which is not equal to E, there is no fixed point of the action. What we mean is that if for P for M, the action of some element on P leaves it invariant, then that means that it must be the identity element. If that is the case, then we say that the action is free. And we will see a counterexample to that very soon. Okay, let's give a counterexample to transitive. So the action of the rotation group on R3 is not transitive, because if you take two vectors, x and x prime, such that their length is not equal, so these are, where x and x prime are position vectors in R3, then if they don't have the same length, x and x prime cannot be connected via a rotation. So that's a very almost a trivial example of how transitivity can fail. On the other hand, the action of SO3 on S2 is transitive. So by applying SO3, we can get from any point on S2 to any other point on S2. However, we know that this action is not going to be free, because we know that, for example, rotation around the z-axis will leave the North Pole and the South Pole, invariant, right? So there are some group actions which will leave some of the points invariant. So it's not a free action, and we'll come back to that. So let's look at what is the definition of a little group. Also known as the stabilizer. So let G be a Lie group that acts on M. So the little group of the point P in M is defined to be the subgroup which leaves P well, invariant, I guess. But what I mean is that H of P, this is the little group of P. This consists of all the elements in G such that the action of those elements on the point P has no effect on it. So in other words, P is a fixed point of the action of H. Okay, the example, of course, is, as I mentioned, SO2, which is a subgroup of SO3. So SO2, say, the SO2 that leaves the North Pole, the North Pole, invariant is the little group of the North Pole. Of course, there are more than one SO3s, inside SO2 is inside SO3, so you have to specify which SO2 is the little group depends on which point you're choosing. So so we now come back to an idea that we introduced before, which is a coset. And now I'm going to introduce the idea of a coset manifold. So suppose H is some subgroup of G, which is, which is a proper subgroup. And now consider the set, which I will denote by G by H, and it consists of all the right cosets so this G of H consists, the elements are the different cosets for the different cosets. So they are not group elements. The elements themselves are themselves sets. So now,
isn't this definition incorrect?
Sorry?
Isn't this definition incorrect?
Right.
Shouldn't it be G, small g element that isn't part of H times the whole group H?
Yeah, no, I mean, you're right. What I'm saying is that, yeah. So if this is just a notation. If I said this is the coset for the element H, this is just notation. Of course, when I'm, as you say, when I'm constructing the coset, the G's I have to consider are in the complement of H. You're right. I'm just saying this is kind of a shorthand notation that.
But I don't understand because we define the coset for the subgroup, not for the element of the subgroup. So you're saying for the H that is part of the subgroup H, but the coset is something that's defined for the whole of H. So not for just one element of H.
Shouldn't it be the other way around?
It's
like
the other way
small
around.
g, big
Sorry?
H?
Small g, big H.
Yeah.
Small.
Oh, I see. Right. Yeah. You're right. So okay. Yeah. Okay. Yeah, I see. Sorry. It should be like this, right?
Yeah.
And
G is
yeah.
in the complement.
Is in G minus H, right? Yeah. Okay. All right. Cool. So.
Excuse me?
Yeah.
I think that G is in G, not G minus H.
What I mean is that G is in the complement of H, right?
You need one element
Not for,
in H for the
not
identity.
really, because else you have
but
no
you-
neutral elements. So
Oh, right. Yeah. Okay. Yeah. Okay.
Of course, the definition, you have many group elements with the same coset, but that doesn't matter for the set to be defined.
Right. Okay. So we say that. So if G1. Okay. So these are the cosets, and this we call it the coset space. So if G1 is in the same coset, we say that G1 is equivalent to G2. So this is an equivalence class. Now, if in our original manifold, G1 was near G2. So they were, we can say that but say G1 is not, they are not in the same coset, then we can say that the cosets corresponding to these group elements are also nearby, and therefore extend, the structure of manifold onto the coset space. So in other words, we can think of the coset space as some kind of a manifold. So why is this useful? And the next example should illustrate that. So suppose we take our friend SO3 acting on S2, and say EZ is the position vector pointing to the North Pole. Now, if G1 and G2 are in the same coset, then if I apply G1 on this vector, I get to a point which is the same point I would have gotten to if I applied G2. So starting from the North Pole, we can reach any other point, say, so by applying a representative of a coset such that each coset corresponds to a unique point on S2. So in other words, the coset, the elements of the coset space are in one-to-one correspondence with the points on S2. So if you had, because the way that the little group is defined, okay, so sorry, I didn't say which coset I'm talking about. I'm talking about the coset which is SO3 over SO2, right? So because of this fact, we can say that I'm gonna just, because this blocks your view, so I'm just gonna write the last part here, is that because any element in a given coset, if I act by those elements on the vectors pointing to the North Pole, it takes me to the same point on the two-sphere. If I take elements from another coset and apply on the North Pole, I will not get to that point. I will get to a different point. Because if I got to the same point, then those 2 points would actually belong to the same coset. So this tells us that we can think of S2 as the coset space. And this has important application both in geometry and quantum field theory. Okay. So when you do spontaneous symmetry breaking and stuff like that, where your some bigger group breaks down to some smaller groups, you will see this sort of structure crop up. So that's why I wanted to cover that. Okay, in the remaining half an hour, I want to shift gear and do the finite dimensional representations of SU2. Like, I believe that almost all of you have seen it, right? So is there someone who hasn't? The ladder operators, the final, and those kind of stuff? So, I mean, I'm asking, should I skip it? Somebody said no, so I won't skip it. It's good to see that. I mean, it's such a nice thing. It's good to see it twice, right? Okay, any questions from the Coset space and things like that? All right. So that brings us into discussion about the geometry of groups. Okay, so finite dimensional representations of SU2. So when you're talking about SU2 Lie algebra, it is very hard to write T's. It's like some sort of deep conditioning. I want to write T, but somehow it becomes a J. I don't know how. So maybe that's because I'm a physicist. So to make the final dimensional representation of SU2s, the first thing we do is that we define what are called ladder operators. And these ladder operators are not Hermitian. So if I take the Hermitian conjugate of J plus, I get J minus, and vice versa. In terms of the ladder operators, the Lie algebra of SU2 or SO3 becomes a part that looks like this, and a part that is the commutator of J plus J minus is 2 of J3. Okay. So the rank of the Lie algebra of SU2 is 1. So we choose the Curtin subalgebra to be just the J3 element. So we label states, well, label vector that it will act on by the eigenvalue, which also in physics is usually denoted by M. So comment is that M is not necessarily a quantum state, it's a vector on which the Lie algebra of SU2 acts. And the other thing to notice is that we are not assuming that m is not assuming that this is an integer. Okay, so that'll arise naturally. So how do we go forward from here? Well, so if we start with the state m, labeled by m, we can ask what happens to the state if I apply on it the J plus operator. So to see this, I apply J3 on it, and then I use this commutation relationship, and then we get J plus J3 acting on M plus J plus of M. So this is J plus J3 acting on the state M gives me M, and this remains the same. So I can write this as M plus 1 J3 of M. So this means that J plus increases the J3 eigenvalue by 1. Yeah. And similarly, J3 acting on J minus of M gives me M minus 1 J minus of M, because of this guy with the minus sign over there. So we see that a picture emerges, and the picture is that the state space or the vector space is one dimension, so it can be seen as a ladder. It's not one dimensional. Sorry, that's a lie. So there is some state M, and there's some state M plus 1. There's another state M plus 2. But there's a state M minus 1, state M minus 2, and it goes on, not indefinitely, because we are looking for finite dimensional representations. And this is like a ladder, and the J plus help you climb the ladder, and the J minus help you go. They take you down the ladder by one step, right? So that's why they're called the ladder operators. Now, we can assume that these states are normalized, and or even like they're. I don't think I'm going to use the orthogonality, but they can also, they're orthonormal. However, there is no guarantee that when you apply J plus, you get M plus 1 without an overall constant. So what is that overall constant? And that is going to play a crucial role in the whole analysis. No need to carry so many papers. So we say, okay, when J plus acts on M, it takes us to M plus 1, but up to some constant, which we say Cm plus 1. And we're going to determine that. So similarly, J minus, when it acts on M, takes us to M minus 1 up to some constant M minus 1. So, Cm and dm to be determined. So consider this object where I know so this is just a number, and the M plus 1 is normalized, so this becomes that. And similarly, if I now consider J minus on M plus 1, then according to our definition of D, the right-hand side should give me D of M times M. Now if I, right, so if I take the conjugate of this, we get M plus 1, J plus, and then I get dm star, the bra of M. And now I take the inner product of this equation with the ket of M. Then this is 1. And we see that the left-hand side of this equation is the same as the left-hand side of this equation. So we conclude that Cm plus 1 is dm star, okay? So we can rewrite this equation, J minus acting on M, as C star of M times M minus 1. Now suppose that M equals to J is the highest possible eigenvalue of J3. So that means that if I apply J plus onto that state, I should get 0. So now, starting with the commutation relation of J plus and J minus, and applying J, to, sandwiching it between J, I get, remember that J plus acting on J gives me 0, so the first term becomes 0. The second term gives me 2J, JJ, right? But this is J minus acting on this gives me right, so yeah. So we get over here CJ star Cj times j minus 1, j minus 1 is equal to 2j, jj. These guys are 1, so I get Cj mod squared is 2j. Okay, so this is the so we get one of the constants. But for generic values of m, okay, so for generic m, if you now sandwich that equation between generic m we get a recursion relationship between the C's and this recursion relationship along with the value of Cj allows us to solve for the CMs. And how do we do that? So we know what Cj is, so we say, okay, we can use this recursion relationship to say, find out what Cj minus 1 squared is, and that's going to be, Cj squared plus 2m, but m now is j minus 1. Right, so this thing is 2, if you put in the value of Cj, it becomes 2j minus 1. Let me not skip steps here. This is 2 of j. This is 2j minus 1. So yeah, so we get 2j minus 1. So similarly, this is Cj minus 2 squared. I'm looking for a pattern here. That's what m is, j minus 2. And if I now put in the value from before, I get 2 times 3j minus 1 minus 2. Now, you can ask, what is C of j minus s of s squared? Note that s is a positive integer. Right? So if you carry this on, you find that it's going to be 2 s plus 1 times j minus 1 minus 2 minus dot dot minus s. And there's a sum here, and if you do the sum, you get which if you simplify, get s plus 1 2j minus s. So this implies that we have Cj minus S. We can choose this to be S plus 1, 2j minus S. Now, as we apply our ladder operator, in this case, if I keep on applying j minus, so I get down, at some point, we want the ladder to terminate because we're looking at finite dimensional representation. But the only way it can terminate is one of these constant going to 0. So at some point, we say, this will be equal to that. That is the only way this thing can go to 0. So this means that the value of j, the highest eigenvalue of m, is s by 2. So it can be either an integer or a half integer, right? Positive integer or positive half integer. The highest value of m. So, so j is a positive integer or a half integer. So this means that m is also an integer or half integer. M doesn't have to be positive, but j has to be. Okay. So now if I write the more, let me come back to the general formula. Oh, man, this is a danger. Like somebody's fingers can, like if you have like big fingers, suppose it breaks. Anyway. There should be a label here, like do not use this when you are inebriated or, Okay, so coming back. So we wrote this we found this. Now it's time to replace j minus s by m. So if I do that, then I rewrite this equation where this had c of m plus 1, then j minus m, and j plus m plus 1, m plus 1. Okay. And similarly, if you have j minus of m, it should give us j plus of m, j minus of m plus 1, m minus 1, right? So this thing is cm plus 1, and this thing is cm star, right? And so this so great. So so from the coefficient, we see that when you go up, when you apply j plus, enough number of times, you get, when you get m is equals to j, right, so yeah, so when you get to say m equals to say j plus 1, there is no more state. So the highest state is, we'll have the label j here, right? And from this you can see that the state that you can get the lowest value of m is going to be minus j. So in total, you're going to have 2j plus 1 states, well, let's say like steps in the ladder, right? So that is going to determine the dimensionality of your representation. So if I pictorially, I come from j to j minus 1 by applying j minus, and then I go to j minus 2 by applying j minus again, and then until I come to minus j plus 1, and then if I apply j minus again, I get to minus j, right? And if you apply j minus again, you get to 0. And if you want to go the other way, you have j plus. Sorry, I'm belaboring the point, but and if I go beyond this, I get 0 again. All right. So I haven't really told you what j is. We only know that j is either an integer or half integer. As you know that j is the eigenvalue of the j squared operator. So the j squared operator acting on m will give you j times j plus 1 times m for any m. And this is a Casimir invariant that labels the whole representation. So now I want to give you some exercises about working out some of the representations. So, 2 small exercises. So if I now give you a value of j and ask you, hey, Patty, can you go and work out the matrices of that representation? Okay, so I want you guys to work this out, right? Because this is where the rubber hits the road. Like, you should be able to do that, right? So yeah, basically, so I will give you some. So suppose I want you to find the matrices for the j equals to 2 representation. Okay. So what are the basis vectors? These are -2, this is the ladder, right? Okay. And then you can find out, what the J3 is. You can find out what J plus is, J minus is, just by, by using this and the, you kind of now know, what you get when you apply with the J plus and J minus J3. So, by choosing, so, I don't want you to do this by hand, do it by Mathematica, but, plus, do it. So we started a little bit late, 10 minutes later, so I'll go on for another 10 minutes. Sorry, no break today. It's very useful. So this is like how to build irreducible representation, right? From scratch. That's what you just learned. But suppose I give you two representations and I say, oh, they represent some different quantum mechanical system and they somehow interact. They have an interaction Hamiltonian. And they form some kind of a bound state. Or they're interacting, we're looking at them from far away. And I want you to tell me what are the possible, what are the possible values of what representation should I expect if I do an experiment, right? And this is known as the Clebsch-Gordan coefficients, method series in quantum mechanics. I will not go there. Don't worry. Your pager due, but we will do. We will generalize that idea, by introducing what are known as what I'm going to call SU2 tensors. So today I will introduce SU2 tensors and some Young tableau, which is really another way of dealing with these tensors. So the kind of question we want to ask is that you have a spin half representation, you tensor with some spin half, another two electrons, say. We know that we get a spin 1 plus a singlet, right? A spin 0. So in group theory language, we write this as 2 times 2 as 3 plus 1. So nobody's going to tell you what notation they're using. You'll just have to guess from the context. So the 2 here refers to the fact that this is a two-dimensional representation, the spin half. This as well, and 3 represent that the spin 1 representation is three-dimensional. So formally, what is a 2 of SU2? A 2 of SU2 is some two-dimensional spinor or vector. So this is living in some two-dimensional complex space. Now, notice that if you have a Lie algebra, so for our case, let's consider, so I'm writing it in a basis where these are Hermitian guys and these are real. If I now consider the complex conjugate of that Lie algebra, and times minus, and I define that to be, say, Ta tilde, you can verify that the complex conjugate, they satisfy the same Lie algebra. So this is these guys form a conjugate representation. Let's call this conjugate. For SU2, however, for SU2, the fundamental and the conjugate representation, so this is also known as the anti-fundamental. I really like this name because I really don't like fundamentalists. So I am in that representation. However, there's bad news. It turns out for SU2, the fundamental representation is related to the anti-fundamental representation through a similarity transformation. And you can verify where C is I times sigma 2, where sigma is a Pauli matrix. So for SU2, so the vector space, so if there was a, like the vector space that the anti-fundamental acts on, we refer it by psi complex conjugated. And for SU2, the notation we use is 2 star. So for SU2, 2 is equal to 2 star. Or 2 is isomorphic or whatever. However, for SUN, for n greater than 3, the fundamental representation, which would be n-dimensional, which I call n, is not equal to the anti-fundamental. So now we'll just pretend, unless we have to do some counting where it's important, we'll pretend that 2 and 2 stars are different for the analysis of tensors. But what's important is that the t's act on some vector space psi A, and t tilde act on some other vector space t star of A, spanned by t star of A. For SU2, these are the same vector spaces. Okay. So say this is an example of a fundamental. So this is 2. And this is under an SU2 transformation. So under SU2, this guy goes like U of A, B acting on B, like this, right? Now, I'm going to introduce some. So you can call it as a vector, right? It's a particular kind of tensor. It's the most basic vector that we can have, or the basic tensor we can have, which transform under SU2. Now we are going to look at some other tensors which are useful, which are known as invariant tensors. And number 1, the Levi-Civita symbols like this. So under SU2, this thing is going to transform as so this gives me a rank 2 tensor, but you see that the definition of a determinant tells me that this is the determinant of U times epsilon AB. But we know that the determinant of U for SU2 is 1, so this is EAB. So we see that this tensor object under an SU2 transformation doesn't change. It remains itself. Now, as I said, I'm going to pretend I know, pretend that the 2 star is a different representation. So the notation that one uses is that the 2 star we raise the index for that guy, and under a SU2 transformation, I'm not deriving all these little things because there's a lot of notation because it'll take too much time. But it's but look into Jones. Jones really, I think yeah, Jones does it, and also Z does it. So under SU2 transformation, this thing goes like U dagger of A tilde A prime A psi of A prime. And this object, because it has indices upstairs, should transform with the U dagger matrix. Again, by the same logic, the determinant of U dagger is also 1. So we get AB. So it doesn't matter whether the AB is downstairs or upstairs. They're both invariant. And lastly, suppose I give you 2 representations. This is a fundamental, and this is, say, an anti-fundamental. And I say, okay, can you make a singlet out of them? You know, what would you do is that you should contract these 2 things, right? And you can show that if you contract these 2 indices, you'll get a representation of SU2 which is trivial. So contracting a downstairs index with an upstairs index is done by another tensor. And this tensor should transform like U, say, B prime, U dagger A prime, delta of A prime B prime. But these are just the inverse of each other. And so it's like if I now use this delta and sum over A prime, I get U of B prime, U dagger of A B prime. So this is just matrix multiplication, which gives me U dagger is U inverse. So I get A of B. So we see that this object is also an invariant tensor of SU2. So these are the invariant tensors of SU2, which will help us build representations. I'm out of time, so I will stop there.
One question here.
Yeah.
Psi A is from 2 star in there, or I got lost in that view.
Chi A?
Yeah, Chi.
Oh, yeah, sure, right. So, yeah, so it could be a different, I'm using a different symbol, but it could be a different 2.
Okay.
And psi B is 2 star. But of course, I mean, we know that for SU2 they're the same because, you know, you can rotate one to the other by using the similarity transformation. But for SU3, they won't be the same. So that's why I'm distinguishing them.